Hey guys, here we are looking at angle similarity. And I think what we need to do is go back and look at perimeter and area of similar figures, because that seemed to be something that we were a little bit confused about last week. So let's take a look at this diagram that we have here. The first question here, it says find the perimeter of PQR. So we're finding the perimeter of the small triangle, and the larger triangle has all the side lengths labeled, which means we can find the perimeter of that larger triangle by just adding up the lengths of the sides. So if we add 15, 17, and 24, we know that the perimeter of this one is 56 centimeters. So when we want to find the perimeter of the smaller one, we don't have all three sides, we only have one. However, the perimeter of similar triangles, the perimeter of one to the other, is just the same as the scale factor. So really all we need to do is set up a proportion. So we are going to set up a perimeter ratio on one side and a scale factor ratio on the other side. So if I know my large triangle has a perimeter of 56, I don't know the perimeter of my smaller triangle, but I do know my scale factor from my large to my small. I'm going to go ahead and use 24 and 9. Those are two corresponding sides. So I'm going to say 24 because I'm going large to small, 24 over 9. And then when I use my cross product or my butterfly method, I get that my perimeter, so I get 24x equals, let's see, what's 56 times 9? 504, and if we divide that out, we get our perimeter is 21 centimeters. That does not tell us any of the side lengths other than the one we already knew, but it does tell us what the perimeter of that small one is because it has that same scale factor. And then on this side over here, it asks us to find the area. Well, we can set that up similarly, where one side of our ratio is going to be the area, and the other side of our ratio is going to be the scale factor. But we have to remember with the scale factor, we have to square it, and I'll talk about that in just a second. So if we have one side of our ratio is the area, so our area of our large triangle, it says, is 126.55. So I have 126.55. I don't know the area of my smaller triangle, so I'll put in X there. And then when we are doing our scale factor, we have 24 over 9. I'm just going to use that same scale factor again. However, our numbers on the right, or excuse me, on the left, are areas, which means I know that they're already squared. They're in centimeters squared. So in order to make our labels match, if you want to think about it that way, we have to square this side. And if we wanted to, just to make it a little bit easier with numbers, we could simplify that fraction on the inside. And so instead of 24/9, we're going to simplify that to 8/3 and then square it. Okay, and don't forget, when you square something, let's leave that 126.55 the same. When you square, you have to square both parts. So we're going to have 64 on the top because 8 squared is 64, and 9 on the bottom because 3 squared is 9. And when we do our cross multiplying, we end up that our area is 17.8 centimeters squared. So the key with our area is to remember we need to square that scale factor. Okay, so just moving ahead now, we're going to think about back to chapter 5 when we proved triangles were congruent. We had all of those different ways we could do that. We had side, 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 angle, angle, side. There are several of them. Now we're going to look at similarity. And there are 3 ways that you can prove two triangles are similar, which just means they're proportional. There is a certain scale factor bigger than the other one. And if two triangles are similar, that doesn't mean everything in the triangles are the same. The 2 things that are important, the corresponding angles are equal. We've already talked about that. And the corresponding sides all have the same scale factor. And there's only three ways to show triangle similarity. One is angle, angle. If two angles of two triangles are equal to each other, then they are similar to each other. And we'll look at that here. That's all we're going to look at today. The side, 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 and side angle side will be for tomorrow. Okay, so like I said, if two angles and two triangles are congruent or equal, then they are similar or they have the same scale factor. So we want to look at these two triangles and ask ourselves, are the two triangles similar to each other based on their angles? Remember, we only have to show that two angles are congruent. Well, we know these two are congruent, right? We know that angle D is congruent to angle G because they're both right angles. However, angle C is 26 degrees and angle H is 64. We don't know, well, we do know that those two are not congruent, but they're also not corresponding. Angle C corresponds to angle K, which means we need to know, well gosh, does angle K equal 26 degrees? So we're asking ourselves, does it equal 26 degrees? Well, let's think about what we know about triangles, and we know that angle G, which is 90, plus 64 plus angle K has to equal 180 because it's a triangle. And we know if we do our math here that angle K equals 24. So yes, that angle is 24, which now we know that angle K equals angle C, and so we have angle similarity. So we could say, okay, first of all, let's just talk vocabulary here. A similarity statement is just saying this triangle is similar to that triangle, which means all we have to make sure is that the corresponding parts are listed in the same order. So if I say triangle, let's see, EDC is similar, one little squiggle mark says similar, is similar to, well, let's see. I said angle E first, and angle E corresponds to angle H. So I'd have to name angle H first. And then I said angle D. Well, angle D is the right angle, so then I'd have G. And my last one would be K, because K and C correspond. So that's how we write a similarity statement. It's just triangle is similar to triangle, and you just have to make sure each of the corresponding angles is listed in the same order. Now, remember from the other day, a statement of proportionality is a set of three ratios where we compare sides, not side lengths, but side names. So we could say that ED, if we look at ED corresponds to HG. That's going to equal the same ratio as DC. Well, DC corresponds to GK. And then CE, that's our third side. CE is going to correspond to HK or KH. Okay, so a statement of proportionality, which some of you guys weren't sure about last week, actually has the names of the segments written as ratios, three equal ratios. Okay, so now we want to know, can you use angle-angle similarity to show the two triangles are similar? Okay, so just a couple of things down at the bottom, some key properties to remember. Okay, first one is vertical angles are congruent. Remember, vertical angles are across from each other. If two triangles share an angle, then that angle is equal to itself. I meant to highlight that, sorry. Then that angle is equal to itself, like by the reflexive property. And if two lines are parallel, like on that second question up there, alternate interior angles are going to be congruent. So if we look at this first picture, remember we just need to have two of the angles be congruent to each other. Okay, so and we are trying to prove, we're trying to show that ABE, let's make sure we know which ones we're actually looking at. ABE, which is this top guy, okay, is similar to the whole thing. Okay, so let's just keeping in mind, sometimes when triangles overlap, it's hard to see what exactly we're looking for. But we do know that in ABE, angle B is 52 degrees, and angle C is also 52 degrees. So we have one pair of angles. We don't have any other information. There's nothing about parallel lines, anything like that, so we have to be a little bit careful. But we do have an angle that they share. So if you look up here, angle A is part of both of the triangles. And remember, if they share an angle, the angle that is in both of them is equal to itself. So we could say angle A in the little triangle equals angle A in the big triangle. So then we know we have two angles that are congruent, so yes, they are similar. If you look at this one on the right, we want to show that basically the little triangle on the left is similar to the bigger triangle on the right. And again, we have these little keys down here to remember. One of them is that vertical angles are congruent. So I'm going to name these because remember it was always easier if we named them. Let's call them 1 and 2. So we know that angle 1 is going to equal angle 2. Well, there's one of our angles. We also have these parallel lines and a transversal, which means that angle 3 and angle 4 here are also going to be congruent to each other. So yes, they are going to be similar by angle similarity. Okay, and one of the ways that you can use angle similarity is when you're setting up proportions. A lot of times the most common example is height and shadows and things like that. So you can use angle similarity to set up proportions. We're going to sketch some diagrams of two triangles. And the reason we have, so basically if you think about this, we have a person here, okay? That person, there's a right angle, okay, and then we have the flag, which we are also assuming here is perpendicular to the ground. So we have an angle and an angle. And if we think about it, you have this line here, and you also have, I mean, if we extend our lines here a little bit, and the ground is one solid line. So therefore, if these two lines are parallel to each other, this angle and this angle are going to be congruent. Therefore, we're going to have similar triangles by angle. Okay, so let's think about how we can use that to set up a proportion. Okay, I'm going to erase some of that extra stuff in there. And if I have, let's see what we know about these people. A flagpole casts a shadow that is 50 feet long. Okay, so this is 50 feet. Okay. And at the same time, a woman standing nearby who is 5 feet 4 inches tall and has a shadow that is 40 inches long. So her shadow is 40 inches. Okay. And she is 5 feet 4. Well, we have a mixture of feet and inches in her height, which means we need to make sure that we are putting it into inches. Since her shadow is listed in inches, we need to make sure her height is listed in inches. So 5 feet would be 60 inches plus 4 would be 64 inches. So 5 feet 4 inches equals 64 inches total. So now we want to know how tall is our flagpole. Well, we can just set up our proportion here where we don't know how tall our flagpole is, but we do know our person is 64. And we also know that our flagpole's shadow is 50 and our person's shadow is 40. So then once we have our proportion set up, we can just use the cross product and see that our flagpole is 80 feet tall. So let's see, we have another flagpole question here. A flagpole that is 18 feet, so let's sketch a little picture. Here's our flagpole that is 18 feet tall. It's got a little flag on the top of it. Casts a shadow that is 10 feet. Okay, and this is good because it's in the same units, feet and feet. How tall is a person? So here's a person standing over here. Okay, how tall is this person? We're going to call that person X feet tall. If the flagpole, if they are standing next to the flagpole and this person casts a 7-foot shadow. And it says you can go ahead and leave your answer as a decimal. We're not going to change that decimal into, excuse me, into feet or anything like that. So if we look at our corresponding pieces, then we have got height of the flagpole, height of the person. So we're going to go 18 over X And then we are going to go shadow of the flagpole over shadow of the person. So then we are going to have 10 over 7. And when we go ahead and solve out our proportion, we get that our person is 12.6 feet tall. Holy cow, our person is, how tall is a person? Well, maybe our person is standing on some stilts if they are 12.6 feet tall. Sorry about that. That might not actually be a legitimate height. I was working with some numbers. So, but we set it up correctly, and we have our proportion set up, which is kind of what we're working with here. Okay, last thing. This is just straight up proportionality. When making homemade noodles, you use 2 eggs for every 3.5 cups of flour. If I use 7 eggs, how many cups of flour will I need? Okay, well, if I compare eggs to flour, this is not so much a similarity. This is just knowing and understanding proportionality. So if I said I have 2 eggs for every 3.5 cups of flour, how many cups of flour would I need if I use 7 eggs? I don't know how much flour I need. So if I go ahead and, again, do my cross product, I would get that it would take 12.25 cups of flour, or 12.25 cups, which would be 12 1/4 cups. If you've ever made homemade noodles, you know it's a big mess with lots of flour everywhere. Okay, so the last one here. I am 5.5 feet tall and cast a 12-foot shadow. If the Statue of Liberty casts a 665-foot shadow, how tall is the Statue of Liberty to the nearest foot? If I compare my height to my shadow, okay, because I'm in feet and feet, and the shadow is 665. So you just have to be careful where you're putting your values here. The height of the Statue of Liberty is on the top, and when you use the cross product, you end up at 305 feet, which I Googled it. The Statue of Liberty actually is 305 feet tall. So a little bit of Google trivia for you. The Statue of Liberty is 305 feet tall. All right, so you will have a class kick over this. Good luck.